Welcome back. In this lesson, we're building a task manager smart contract, the next step in your Sorban journey. So if you've completed the guestbook tutorial, you already know some critical patterns we'll use today. If you haven't, I recommend pausing and completing that first, as we'll build directly on those concepts. Let's see where we are. The Hello World taught us basic contract structure. The increment introduced storage, and Guestbook taught us authentication and typed storage keys. Today, Task Manager adds state management and complex authorization. Each tutorial builds on the previous one, so you're getting a solid foundation. So, what exactly are we building? A task manager contract, and it does the following. It creates tasks with descriptions. It tracks whether tasks are pending or completed. Mark their own tasks as complete. And prevent others from messing with the tasks. Think of this like a to-do list but on a blockchain. Here's the key concept. Tasks have a life cycle. When created, they start as pending. Users can mark them completed. Once completed, they can go back to pending. And critically, only the task owner can make these changes. This is called a state machine, and it's fundamental to smart contract development. Before we dive in, make sure you have completed the guestbook tutorial. Seriously, this is important. And you have your code editor ready. You have basic understanding of authentication with require auth and familiarity with type storage keys. We learned this in guestbook. If any of these are missing, pause the video and get set up first. By the end of this tutorial, you'll know how to use enums to represent different states, implement state machines with transition rules, add complex authorization, not just are you authenticated, but do you own this resource, update existing data safely in storage, return success or failure indicators instead of just panicking. These patterns show up everywhere in blockchain development, so pay attention. In Guestbook, we learn how to store data and authenticate users, but that contract had a limitation. Messages were append only. Once posted, they never changed. What if you want data to evolve? What if a task starts as pending and becomes completed? What if the owner should be able to make that change? That's what we're solving today. 3 key questions. How do we track whether something is done or not? How do we prevent Alice from completing Bob's tasks? And how do we prevent marking a task complete twice? Keep this in mind as we build. Let me introduce you to state machines. Think of a traffic light. It can be red, yellow, or green. It's only one of these at a time. Each transition is in a specific order. Green, yellow, red, green. It can't skip states or go backward. Our tasks work the same way. Pending or completed. Pick one. New tasks only start with pending to completed. Can't go back from completed to pending. That is a state machine, and we'll implement it using Rust enums. Here's something critical. We need 2 levels of security. Level 1, authentication. Are you who you say you are? This require auth. You learn this in Guestbook. Level 2, ownership. Do you own these specific tasks? This is new. we check if task owner equals the caller. So why both? Authentication proves you're Alice, but that doesn't mean you should be able to complete Bob's tasks. We need both checks. This is the difference between simple and complex authorization. All right, let's start coding. Let's create our project. Stellar contract init name task manager. All right, so we have created our project, and now we're going to make our changes. First, our import. We need to import what we're going to be using, the tools we're going to be using in our project. It won't be much different from what we use in the guestbook. So let's go ahead and do that. So we need contract implementation, contract type, what else do we need? We need log, address, address, so a quick recap, we're using no std because we're compiling to WebAssembly, and we're not going to be using the standard library, and we import Soroban SDK with macros, the following macros: contract implementation, contract type, and the log, environment, string, and address. Now here's where we apply what you learn in guestbook, which is the type storage keys. Remember how guestbook used a data key enum instead of a string or a symbol? We're doing the exact same thing here. So let's go ahead and create our key. As you know by now, we start by using this following macro: contract type, derive clone, public enum storage key. We'll have the following: the task count and the task ID, which will be a U32. Let me break this down. The contract type tells Soroban that this enum can be used in storage, same as guestbook. And task count, this variant stores the total number of tasks, just like data key count in guestbook. And we have task 32, U32. This variant stores individual tasks by ID, just like data key message U32 in guestbook. So we have task 1, task 2, task 3, so on and so forth. And we only need to clone here because we will need it in the storage operations. So it's very much the same as the exact same pattern as what was used in the guestbook smart contract. This is why learning guestbook first was important. Now for our first new concept, we're going to represent state with enum. Okay, let's go ahead by creating an enum called task status, which will either be pending or completed. Let's go ahead and code it. Contract type, derive, debug. We also need to be able to debug, clone, EQ and EQ. The name of the enum, pub enum task status. It will have the following state. It's either pending or completed. This is how we implement our state machine. A task can be either pending or completed, never both, never neither. See, the partial EQ is crucial because we need to compare statuses like if task status is equal to task status completed. Without it, that comparison won't compile. And debug will help us to print statuses in tests, which will be very useful for debugging. So why enum instead of a boolean? A boolean can only have two states, either true or false, 0 or 1, which is very limited. But enum can be extended, not just pending complete and completed. We can add in progress, we can add cancelled, on hold. So boolean is limited, but enum, with enum we can expand to however we want. Now let's define what a task actually is. For that, we're going to create a struct, a task struct. As usual, we start with contract type, derive, debug, clone. Public struct task, and a task will have the following: pub id u32, pub owner, address, pub description, string, pub status, and you can imagine what its status is, because the status can either be pending or completed. So we're gonna be using this enum task status. So the ID is a unique number, just like message IDs in guestbook. Owner is the address of who created it. It's critical for authorization. Description is what the task is about, which is going to be a text, and the status is our enum, which could either be pending or completed. This is the key difference from guestbook. Guestbook messages didn't have state, they were static. Tasks have state that changes over time. That's what makes this more complex and more interesting. Now let's set up our contract, same as always. So our contract name is task manager. And under implementation, we implementing task manager. And our function will go here. So we have an empty struct, which is the implementation block. You know this from every contract. And the data lives in storage, not in struct. Now let's create our first function, and this will be, we want to create the tasks. So let's go ahead and create our function, public function create task. So this will do the following. We have env, we have owner, which is going to be the address of the person creating a task. Type address, and we have the text, description, will be type string. But here we want to also do something very special, something that is a bit different from what we did before. We'll return an integer, an i32, whenever we create a task. So why is that? Why do we return a number? Why do we want to do this? So in guestbook, post message, when we use the post message function, it returned nothing. But here we are returning a number to know which task was created, and it also allows us to reference it immediately. Let's go on. So what do we put in our first line? We authenticate. So we're going to authenticate the owner to make sure it's the owner. Require auth. So the first line only is authenticate. You know this pattern, never trust the caller without proof. And now next step, we're going to use our count. So let mute count u32 equal env. So we want to get what's in this current in the storage. Env storage instance, and here we are getting, so get and we're gonna get our count in the storage key. Storage key, the task count. But if currently there's nothing in the task count, the default will be 0. So the default for count will be 0. So unwrap or 0. This is very similar to what we did before. We're using storage key task count, and here notice we're using a ampersand, which means we're passing a reference. The storage system takes a reference to our enum variant, and an unwrap or, which we used before, means if nothing is stored yet, use 0. This handles the very first task gratefully, no panic, just default to 0. Next, we're going to increment our count. Count plus equal 1. So this is an increment to get the next ID. First task gets 1, second will get 2, and third. So this is the same pattern as guest book. All right, now let's add something to our task, to this particular task. So we do that by creating a variable task equal task. Our ID will be the count, and we have owner. It should be owner. I will clone it. We also have description, and we have status. But what will be our status? I want you to think about it. What's going to be our status at the moment? Is it going to be completed or pending? The correct answer is pending. So this is critical. We're forcing new tasks to start as pending. We don't let the caller choose the initial status. Why? Because we control the state machine. Task must only start pending, then transition to completed. If we let callers to create already completed task, our state machine breaks. Does that make sense? Next, we're going to do the following. We're going to store the task under storage key task count, and we're going to store the updated count under storage key task count. Okay, I'm going to show it in action. So we're here. We're just going to do what we've done so many times. env storage instance set. What are we setting? Storage key tasks count, and this is going to be our value. So we're going to add this new task. And we're also going to store our count so that we can retrieve then at the next create. So to do that, we env. Let me just copy and paste. Env storage set, instance storage set. In this case, we updating the task count. And the value will be count. The value is count. Next, we're going to use log to help us to see what's happening on chain for debugging purposes. So let me see if I imported log here. Yes. So log task created with ID. It's gonna be our count. Yeah, that's it. And the last thing we need to do is return our ID of this created task. So we're simply going to do this. There's something that is off here. Forgot a semicolon. All right, this next function is where things get interesting. Complete task has 4 levels of checking. Is the caller authenticated? Does the task exist? Does the owner, that's the caller, own this task? And is the task not already completed? Only if all 4 pass do we update the status. So let's build that step by step. So let me repeat that again. You're creating a function called complete task that has 4 levels of checking. So the first checking will be, is the caller authenticated? The second check will be, does the task exist? Third, does the caller own this task? And 4, is the task not already completed? So we're going to do that next. Public function complete task. I will take the following parameter. So env as usual. The owner. Just the address. Task. And the task ID. Now we have a task ID. This is a type U32. And here we're going to return a boolean because we expect some failures. It's either going to be some success or failure. So we're using boolean. For example, if the wrong owner tries to complete the task, so the expected will be false. The task is not complete. If the task is already completed, then we also expect a false because it's already completed. We're going to check the owner. We're going to use authentication. So let's do that here. That's going to be the first line in our function. So owner dot require auth. This prove you are who you say you are, but this alone isn't enough. Keep watching. Let's check if a task exists. So we're going to do the following. Let mute task equal env dot storage dot instance dot get. So you want to get the task ID. So and storage key task ID. And if it does not exist, if the task is not existing, then to your panic, we expect task not found. Now we want to check if the caller of this function actually owns this task. So to do that, we're going to use an if task owner is not the owner. This is why we use the EQ here. So this is what is helping us. If task owner is not equal to owner, do the following. We're going to log this following an unauthorized caller is not task owner. Return false. So just to explain, the owner is whoever is calling this function right now. So let's say this is Bob. Bob is calling this function. So if Bob is calling this function and is trying to complete Alice's task, then we return this unauthorized caller is not the task owner. So that's basically what it's doing. Now we're going to check if our task is already completed. And to do that, if task status is equal to task status completed. We're going to log the following: log the task already completed. Return false. So now we're comparing our current status to completed. So if it's already completed, we can't complete again. Now that we have done all these checks, we can actually now complete our task. To do that, with the following task dot status equal task status completed. But there's something that we haven't done here that is very important. We've only updated the status to completed in the memory, but not in the blockchain itself. So we have to do that now, because the storage on the blockchain hasn't been updated. So we do what we've done so many times: env storage instance dot set and storage key task ID and task. Alright, now our blockchain has been updated. We're now going to log it env task and then the task ID marked as completed. And if you have done all these, we're now going to return something. All these tests, all these passes checked successfully. Now we can return true. And notice we're not using a semicolon. So now we can go on. We also would like to retrieve task, to view task by the task ID. So we're going to create a get task function to do that. So public function get task env task ID, so U32. Going to be returning a task whenever we call it. Env storage instance get, going to the storage key, the task, and task ID. If there's nothing there, then this will be the default. Expect task not found. It will also be useful to get the task count, the current task count, and we do this by creating a function called get task count. Returning a U32, and now we're going to go to the environment to get the current count. Env storage dot instance dot get. And how do we get the count? We go to the storage key, and task count, or else if there's nothing, then it's going to be 0. Simple as that. That's why we're going to be returning. This is identical to get books, get message count. These patterns are consistent across contracts, and that's intentional because we're learning upon what we've already learned. Now let's see our smart contract. Let's save it and see what we've done. We have type storage key with storage key enum. So we have the task count and the task ID. We have state representation of the stack status, can either be pending or completed. We have our data structure, the task struct with the ID, the owner address, string, and the task status. The task manager, that's the name of our smart contract, and this is the implementation of our functions. And something did wrong here. Let's see. All right. We have the following functions. You can create a task, and this is why we did to create a task. We complete task, can get task, and get the task count. Now that we have done this, we can now head over to testing. Just like we done in the guest book smart contract, here we're going to import the test utils so we can be working with different addresses. So let's do that here. Test utils address as underscore. We have env and we have string as well. So now let's make our changes here. We're using the task asma contract name is task manager. So just copy that task manager, and we remove this. Okay, so now let's generate our owner. So let owner equal address generate env, and let's description equal string from str and hello there. So this is going to generate an address and create test data that we're going to be using. And one more thing that we need to do is add this very critical line, env mock all authentication. So env mock all auth. So this will mock authentication because without this our test will fail because we don't have real signatures. So in tests we want to test logic, not cryptography, so we use mock authentication. So now that we have this, we have the owner, we have the description, let's create our task. Let task ID equal client dot create task, owner, and description. So notice we capturing the return value. The function returns the task ID and we store it in task ID. So now we see if that task ID exists. So assert task ID, we're expecting 1 because we're creating our first task. And we can also call our get task count, assert client dot get task count, and for the first call we also expect a 1. Very basic assertion. Now let's verify everything about task. And let's test it. So everything passed. Now we can go further and use very different tests and different cases, and let's go ahead and do that. So this is a more comprehensive test. We have the test 1 is create a single task and verify all fields. Now we have test 2, create multiple tasks across different users. The test 3, complete a task successfully. Test 4, attempt to complete a task twice, should fail second time. Test 5, unauthorized users cannot complete another user's task. We also have getting a non-existent task should panic. Completing a non-existent task should panic. Initial task count should be 0. Comprehensive ownership test, multiple users creating and completing task. So there's all these different text. The more, the merrier. So now let's test it. So we've passed all our tests, and now we can go to the next step. Thank you for watching this video.